Hello, everyone. Hey, good afternoon. Welcome back. So, I haven't actually received any questions for integration yet, which is very worrying because this is typically the hardest chapter. So, I was expecting a ton of questions, but I haven't gotten a single question. Hello, guys, you gotta do the work. All right. Anyway, since I haven't received any questions yet, I shall start a new chapter. Differential equations. So this chapter kind of depends on you knowing differentiation and integration very well. So if you haven't done any exercises on those two chapters, you're going to find this really difficult because it all builds on that. But if you have, good job. Give yourself a pat on the back. All right, let's get started. So, what exactly is a differential equation? So there are actually many different forms of differential equations, but the one that we're learning here is the simplest one. The one that we are doing is going to be a first order linear separable. I misspelled that. Separable differential equation. If you're doing further maths, you will eventually encounter second order differential equations, but we're not gonna bother with that here. So, differential equations actually show up in many different areas of physics and science in general. So, take the temperature change of an object. So, for those of you who have done a bit of physics, you would know that that the larger the temperature difference between two objects, the faster they would achieve thermal equilibrium. Okay, so you can say that the rate of change of the temperature of an object is going to be proportional to the difference of the temperatures. So you could put something like, initial temperature minus current temperature. And because they are proportional, you can write it as a equation by introducing a proportionality constant, like using the Hooke's law, right? Spring constant. So there we go. Another example of a differential equation is, let's say you have an object falling. So you would have, let's say this is the object falling from speed v, and this is the weight of the object, and it is being opposed by air resistance, right? If you've done a bit of physics, this would be familiar. If you haven't, don't worry, because you don't really have to know this. I'm just showing you some examples from physics. But eventually you would have to learn this anyways, even if you're not taking physics, because you will have to do mechanics after paper 3, which is basically physics. Okay, anyway, so you know that to write the resultant force equation, you have to write W minus F, right? And then W is mg, and then F is actually the friction, which depends on how fast you're moving through the air. So it's proportional to the speed squared. And this one is actually ma. So this is actually a differential equation in disguise, because a is actually d2x dt squared. And then v is actually dx dt, and then the whole thing squared. So this one is an example of a second order differential equation, which is thankfully not in your syllabus. But as you can see, a lot of the equations in physics, they all can be boiled down to differential equations, and you can actually solve these equations if you know what to do. So anyway, hang on, let me make my pointer a bit bigger so I can actually point at things. I mean, you guys can actually see my pointer, right? If I'm moving my pointer around. I've been going with the assumption that you can, but maybe I've been mistaken. But you should be able to see my pointer moving around like this. Okay, anyway, so let's see. Let's do an example of a differential equation. Let's say you have dy dx equals to x squared x squared plus e to the power of x. Okay, this is a very simple differential equation. So how do you solve for x? So solve this guy. So what you want to do is you want to put all the x's on one side, all the y's on one side. So basically you can split the dy dx into something like this. Okay, I've just multiplied both sides by dx. At this point you might be wondering, hang on a second, is that even legal? Can we even do that? Yes, you can. Okay, so what you want to do after you do this is you want to integrate both sides. So on the left side, you are integrating 1. On the right side, you're integrating x squared plus ex. Okay, so this guy, you integrate 1, you get y. This guy, you get x cubed over 3 plus ex plus ac. So there you go. This is the solution to your differential equation. But typically, we refer to this as the general solution because we have a c over here. So if your c is an unknown, we refer to it as the general solution. Okay? Now, there's also another kind of solution called a particular solution. That is when your c is not an unknown. So sometimes in the question, they would say, given that x equals 1 when y equals to 2, find the particular solution. Okay, so all you have to do is you substitute that into your general solution. So you get 2 equals to 1 over 3 plus e plus c. Therefore, c must be equals to 4 over 3 minus e. Okay. I would recommend leaving it like this. So if you have e or pi, I would not recommend leaving it in decimals. Always leave it in third form or an unsimplified form. Basically, don't leave it as decimals if you can help it. Okay? And then once you get your c, you can substitute that into your general solution. And there you go. That is your particular solution. Done. This is your particular solution. Okay? That's it. Now, let's show you a more complicated example. Right. Another example. Let's say we have dy dx equals to xy. And then they want you to find the general solution. Or you know what? Let me say find the particular solution when x equals to 2 and y equals to 3. Okay, there we go. So the first thing you do is you separate all the y's and put them on one side, separate all the x, put them on the other side. So we have dy and then 1 over y, and then x dx. Okay? And then I'm going to integrate both sides. So on the left side, I'm going to get ln modulus y. On the right side, I'm going to get x squared over 2. And I'm going to get plus c. Technically, there are 2 plus c's. There's actually a plus c here and a plus c there. Okay, so what I've actually done is I've moved this plus c over. And then I've named c2 minus c1 as c. So I only have to write one integration constant, 1c. Okay, so once you've done this, you want to substitute your values in. So this is the usually they call this the boundary conditions. Boundary conditions. You don't really have to know this, but I'm just telling you. So now we're going to substitute that in. We're going to get ln 3 equals to 2 plus c. Therefore, c is equals to ln 3 minus 2. All right, and then we're going to take that. We're going to chuck that into our general solution. And then we get this guy. And we're done. There we go. Finished. Woohoo! Okay. Let's see if we have some more other examples here. Let's see. What else can we do? Sure, why not? Let's do this one. So let's do one more example. This one is actually not that difficult. So we have dy dx equals to e to the power of negative y. So you can see there's no x in there. But the way you do this is the same. You put all the y's on one side. So in this case, you would have ey dy equals to dx. And then I integrate both sides. There's a 1 over here. Then this guy gives me ey. This guy gives me x plus c. Okay? And then usually what you want to do is you want to make y the subject. Okay? So what you want to do here is you ln both sides. So you get y here. This guy will be ln modulus, and there's no modulus, sorry. Ln x plus c. And this guy is actually y equals to ln x. Oh wait. Oh yeah, you just leave it like this. You just leave it as ln x plus c. Yep, that's good enough. So there you go. Done. Okay. What else? Okay. Let's find some other questions on the past years. There we go. All right. So the coordinate xy of a general point of a curve satisfies the differential equation blah 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 blah. For x greater than 0, it is given that y equals 1 when x equals 1. So this is the boundary condition that they've given you. Solve the differential equation, obtaining an expression for y in terms of x. Okay, so this is a pretty standard kind of question that they can ask you in the exam. So you don't really have to identify what kind of differential equation is this, unlike, in further math, because there's only one kind of differential equation in math. It's a first order linear separable differential equation, and the steps always follow the same method. So all you gotta do is you separate all the x's. So in this case, you would have x over 1 minus 2x squared. Oh, sorry, hang on, I messed up. Oh, we have 1 over y dy equals to 1 minus 2x squared over x dx, and then you integrate both sides. Okay, so on the left side, we can integrate that fairly easily, but on the right side, how do you integrate something like this? So usually what you want to do is you want to try to write it in this form, 1 minus 2x squared, and then x, and then minus 1. And then the thing with a power that is not 1, you can try to substitute it and see whether you would get, u prime out here, right? Whether differentiating the thing inside the bracket will give you the thing outside the bracket. In this case, it doesn't. So you can't use integration by substitution. Another thing you could do is you can see that you can actually split this up into two terms, 1 minus 1 over x minus 2x squared over x. So you want to do that first, okay? And now you can actually integrate normally, because this is actually something that you can integrate fairly easily. So on the left side, you're going to get ln modulus y. On the right side, you get ln modulus x minus x squared plus c. Okay, and then now we're going to substitute our boundary conditions inside to find c. So we're going to get ln 1 equals to ln 1 minus 1 plus c. So therefore, c must be 1. Therefore, my general solution, my particular solution is going to be ln modulus y equals to ln x minus x squared plus 1. But you can see the question wants you to express y in terms of x. So your y must be the subject. So we're going to have to get rid of this ln here by moving ln to the other side. So when you move ln to the other side, it becomes e to the power of ln mod x minus x squared plus 1. Something like that, okay? And if you want to simplify this further, can you simplify this further? No, I think this is as good as it gets. So there you go, done. Okay. There's actually one kind of differential equation question that I haven't gone through with you guys yet, so I'm going to try to find it on the past years. Not this one. Yeah, sure. Let's do this one as well. It's not the kind of question I was looking for, but I think it's still good exercise to do this. Okay, I'll paste this here. All right, so we have a differential equation. We are given the boundary conditions, and you want to find x in terms of t. Okay, fairly standard. So again, we're going to move all the t's on one side, all the x on one side. So we have 1 over cos squared 2x dx equals to 1 over e3t dt, and then we integrate both sides. Which is why I was saying that you need to be very familiar with all the different forms of integration from the last chapter if you want to do the later chapters. This is one of them, okay? Because you can see a lot of these involves integration. So you can see on the left side, you actually can write this as secant squared 2x dx, right? On the right side, you can write it as e to the power of negative 3t dt. So what happens when you integrate secant squared? Well, we know that if you differentiate tangent, you would get secant squared. So integrating secant squared should give you tangent, right? And you want to make sure that this guy is a linear function. Yes, it is a linear function, which means whenever you integrate secant squared and then some linear function, you would get tangent, the same function, and then you divide by the derivative of the function plus c, right? We discussed this in the last chapter. So let's do that. We're going to get tangent 2x over 2. There's a plus c, but we're not going to write that because we have another plus c on the right side, which we're going to combine that with. So what happens when you integrate e to the power of some function? So remember, whenever you integrate e to the power of some function, you would get e to the same function divided by the derivative of the function plus c. And remember that all this can only be done if the function is linear, which it is in this case. So lucky us. Woohoo! So we're gonna get e minus 3t over negative 3 plus c. And now we can substitute in our boundary conditions. So we're gonna get tangent 0 over 2 equals to e to the power of 0 over minus 3 plus c. Tangent 0 is 0, e to the power of 0 is 1, so c must be 1 over 3, okay? And then we're going to chuck that back into our original equation here. So we have half tangent 2x equals to negative 1 over 3 e negative 3t plus 1 over 3. So remember, the question wants you to write x in terms of t, which means you have to make x the subject. So I'm going to multiply everything by 2 and then move the tangent over. So we have negative 2 over 3 e negative 3t plus 2 over 3, and then the whole thing, there's an arctangent here. Okay, and then x is going to be equals to 1 over 2 arctangent bracket 2 over 3 minus 2 over 3 e negative 3t. And there you go, done. Okay. Okay, so if you look here, sometimes they ask you something like this. State what happens to the value of x when t tends to infinity. Just put that here. Well, let's see. You can see this is an exponential function. So when t is a gigantic number, what happens to this this value here? You have e to the power of some negative, some huge number. So you can always put that in your calculator to see what happens. You get e to the power of some negative, let's say negative 10,000. You will get something very close to 0. In fact, your calculator will just show you 0 because it's that small. So if this thing becomes 0, then so you can say that the limit as the limit as t approaches infinity, x is going to be equals to half arctangent 2 over 3. So arctangent 2 over 3 times 1 over 2 gives me 0.294. There we go, done. Make sure it's in radian mode. Okay? Because the 2 over 3 is not in degrees. There. And done. Okay, let me see if I can find the question that I was looking for. No, not this one. Hang on a bit. Haha, yes, I found it. Okay, yeah. This is the kind of question that I would say it probably as the hardest kind of question that they can ask you for this chapter. All right, let me just move this down here. Okay, can you guys see it? Is it too small? Try to make it bigger. There we go. A certain curve is such that its gradient at the point xy is proportional to y over x root x. The curve passes through the points with coordinates blah blah and blah blah. By setting up and solving a differential equation, find the equation of the curve expressing y in terms of it. 8 marks. 4. Okay, so if you know what to do, it's actually very easy. But here you can see they haven't actually given you the differential equation. So you have to work out the differential equation first. Now, they've actually given you a hint here. They're telling you that the gradient is proportional to y over x root x. So those of you who have done a bit of physics knows that you can actually write it as dy dx is proportional to y over x square root of x. If you haven't done physics, then I'm telling you what to do. There you go. That's what you want to write out in the first place. That's what the statement tells you, okay? And then once you've written out the statement, you want to change this proportionality relation to an equation. So to change it to an equation, all you have to do is introduce a proportionality constant, which I'll call k. There, done. So now that we have found our differential equation, we can solve our differential equation. But notice that now we have an additional unknown k. And then once you integrate it, you would have two unknowns, k and c, in addition to y and x. But it's fine, okay? So first we're gonna move all the x's to one side, all the y's to one side. So we have 1 over y dy equals to k, 1 over x root x dx, and then we're gonna integrate both sides. So on the left side, it's fairly straightforward. We just get ln modulus of y. On the right side, you can actually rewrite this x root x here as, you know, let me get rid of this. This whole thing is to the power of -1. And then I can also remove these guys here because basically we have x to the power of 1 times x to the power of a half, which is x 3 over 2. And then when I times the -1 in, I would just end up with x to the power of -3 over 2. So integrating this guy is going to give me 1 over 2 and then divided by -1 over 2 plus c. So we're going to simplify this guy a bit. We're going to get ln modulus y equals to -2kx -1 over 2 plus c. Cool. So now we actually have two boundary conditions. See, they've given you two boundary conditions, 1, and 4e. So we're going to substitute those in and solve simultaneously, okay? So we're going to substitute 1 in. At 1, we're going to get ln 1 equals to -2k times 1 plus c. And simplifying this, we are going to get 2k is equals to c. And then at 4e, what do we get? We get ln e equals to -2k times 4 to the power of -1/2 plus c. So ln e is just 1. 4 to the power of -1 over 2 is 1 over 2. So we get -k plus c, which eventually simplifies to k is equals to c minus 1. Okay, so now we have this equation and this equation. We're going to substitute the second equation into the first equation, and we're going to get 2 times c minus 1 equals to c, which is 2c minus 2 equals to c, and we're going to get c is 2. Hey, we found c, so now we're going to take this guy, and I'm going to chuck that into this guy, which gives me k is equals to 2 minus 1, which is 1. Oh, we found k. Excellent. So now we can write our particular solution of the differential equation, which is going to be ln modulus of y equals to -2x -1 over 2 plus 2. But we're not done yet because the question wants us to express y in terms of x. So we have to make y the subject. So we're going to make y the subject, which means you have e to the power of -2x -1 over 2 plus 2. And you can actually simplify this a little bit further by writing it as e squared times e -2x and then -1/2. And yeah, I'll just leave it like that. E squared is actually, what's E squared? E squared is about 7.39. So I could leave it as 7.39 e -2 over square root of x, if I want to, but you don't have to. You can actually leave it like this, it's good enough. Okay, so there you go. So sometimes you have to construct your own differential equation, but the trick here is just to write this and then change this to this by introducing a proportionality constant. That's all you have to do, okay? And again, they have this question here, describe what happens to y as x tends to infinity. Okay, so what happens to y as x tends to infinity? So, as the limit of x tends to infinity, what happens to y? Well, y is going to be equals to, okay, so if you look at this here, if x becomes infinity, you'll be dividing by infinity, right? That means this thing would be very close to 0. This fraction here would be close to 0. So e to the power of -0 is just 1, which means y is going to approach 7.39 because this e thingy here is going to be 1. Okay, so there you go. Done. Okay. That's it, really. That is all the things that are related to this chapter. It's actually a very short chapter, but I would say it's the difficulty of the chapter depends on how well you understand integration, the chapter before this. So, but yeah, as far as things that are unique to this chapter, we have actually covered everything. There's nothing much to it. Okay. So, next class we are going to do numerical solutions of equation, which is again a very short chapter, so we can probably finish that in one class. And then after that, we will move on to we could do complex numbers or vectors. We'll see what happens. Or maybe I'll let you guys choose because that will be our last class together. So that will be on Thursday. So Thursday will be the last class I'll have with you. Next academic year in September, Mr. Zikri will take over. He will take over maths and physics. Okay, so I've already briefed him on where we are stopping, so he should be picking up where we left. Okay, yep, that's it. So, those of you with the textbook, you can actually try exercise 9C. Okay, you can do 9B as well, actually. 9B and 9C. Yep. 9A, don't really have to do that. You can skip that. Not really important. So 9B and 9C. Yep. Okay, let me just write that down here. Try 9B and 9C. Okay. That's it. So, I suspect most of you haven't done the chapter for integration yet because I haven't received any questions, and typically that's the chapter that I get a lot of questions from the last 4 batches that I've taught. Usually people ask me a lot of questions. So either you guys know everything or you haven't done your work. So I think the latter is more likely. So I shall leave you to do those questions, and I will be expecting questions from you guys. Okay? All right. that's all for today. What is going on here? Why is there like a thing over there? That's strange. What is this? What is going on? Oh, that's the chat box. Reload. Yikes. Why is my chat box not working? Streamlabs is broken. Okay, whatever. Doesn't matter. So anyway, I'll see you guys tomorrow. Bye-bye. Bye-bye. Those of you taking physics, I will see you later at 3. Latest. Bye-bye. Oh. Okay, yep. See you.